Hi students, welcome to the second topic on chemical bonding. This topic will be a little bit different from what you have learned in secondary school. In fact, it is very different. So I often share with your seniors that the best way to learn this topic is to discard what you have learned in secondary school and to embrace it as though it's an entirely different topic, or it's a topic that you have not seen before in your whole life. Because sometimes having the baggage of what you learn in secondary school might impede your learning in chemical bonding. Yep, so perhaps you want to bear this in mind, and perhaps might be good to throw away some of the, if not all the concepts that you have learned in secondary school. Yep, okay, and this topic will span around 3 to 4 weeks, but do not expect you to have perfect mastery at the end of the third or the fourth week, because it is very difficult to understand every aspect of chemical bonding by simply just going through the lectures, as well as simply just going through the exercises. Sometimes you need to develop that chemical intuition, and time is a very important factor. So you might need a few months to fully appreciate what you have learned in chemical bonding. So do not be upset if at the end of 3 to 4 weeks you feel that you are still not very sure about a lot of things in chemical bonding. This is usually the case. Some of you will be ahead of others, so do not just be mindful that some of us will need more time to understand. Yeah, so do give yourself that time. Do not just jump into feeling that you have to understand everything from day one. Okay, there are quite a lot of learning outcomes. It spans over a few topics from a syllabus document, largely from topic 2, but you also have some from topic 7 under energetics. Okay, and as well as topic 5 and even in topic 11 under organic chemistry. So unlike most other colleges, we are going to introduce to you the concept of hybridization right over here in chemical bonding, so that you have a earlier introduction of this concept, and then you think about it over a few months, and then once you are introduced to organic chemistry, life will be a lot easier. Okay, yep. So I'm just going to jump straight into the introduction. Perhaps let me just say this categorically, maybe from day one, that all forms of chemical bonding are electrostatic in nature. Yep. This might be a bit different from what you might be expecting, because perhaps in secondary school you are aware that for metallic bonding, it originates from the cations, the interaction between the cations and the C or D localized electrons. So if I tell you that it is electrostatic in nature, you will be convinced by it, because, well, cations are positively charged, electrons negatively charged. So I think you'll be happy with acknowledging that metallic bonding is electrostatic in nature. Yeah. So if you recall ionic bonding, that's between a positively charged ion known as a cation and a negatively charged ion known as an anion. Yeah. So telling you that is electrostatic in nature, I think it is also straightforward, because that's between something that is positive plus and something that is minus. Yeah. But for covalent bonding, that might be something that you are not very familiar with, because sometimes in secondary school, in the needs to rush through certain curriculum, or perhaps when you're doing a revision, you might overlook certain things. You are introduced to the fact that covalent bonding involves sharing of electrons. So when you're looking at sharing of electrons, it might not come to you as electrostatic in nature. Yeah, but the truth is that because of the sharing of electrons, the electron pairs, it could be 1 pair or 2 pairs or 3 pairs, right? They are being maintained by the nucleus. So the electrostatic forces of attraction is actually between the shared pairs of electrons and the nucleus. Yeah, so covalent bonding is also electrostatic in nature. That is something you need to be aware of. Yeah, and that is nicely being introduced under this section. Okay, yep. So sometimes you might be misled by some of the drawings. Like for example, over here for the ionic bonding model, right, we draw the cation as a circle and the anion as a circle, and then it seems that the cation is touching the anion, but of course in actual fact they do not exist as tangible spheres. You know that they are simply just electron clouds interacting with electron clouds. Okay, yeah, so the sphere we are drawing here is just a representation. It doesn't equate to reality. It's the same as this particular sphere we are drawing over here. Yeah, but there is a need for you to know how to represent them on paper. Yeah, so that is why we have a figure 1 to show you how you could possibly draw them. Okay, yeah, I use the term how you could possibly draw them, but of course under the individual topic we will showcase maybe a more accurate way of representing them. Yeah, but this is just an introduction, so it's something that you might want to take note of. Okay, and of course they are not drawn to scale. Yeah, just be aware of that. Yeah, so some appear smaller, some appears bigger. Like for example, you know that the nucleus, if the nucleus is analogous to a pinhead, then the electron cloud will be analogous to the perimeter of the stadium, something along those lines. Yeah, so obviously they are not drawn in scale. Yeah, so you need to be aware of the limitation of representation on paper. Yeah, because we definitely do not want the students to go away with the thinking that atoms or ions are like sphere-like, etc. You know, like they are not tangible. Okay, yeah, so they are just representation on paper. Right, so over here we have table 1, which compares between the different types of bonding in terms of the strength. So as you might already learn in secondary school, ionic, covalent, and metallic bonding are what we call intramolecular bonding. Okay, so this bonding are intramolecular in nature, so I just put intramolecular. Yeah, so intramolecular here means they exist within the structure. So for example, covalent bonding is within the molecule, then metallic bonding is within the giant metallic lattice, ionic bonding within the giant ionic lattice. Yeah, so this interaction tends to be really strong. Yeah, so if you look at them in terms of kilojoules per mole, it ranges from 400 to 4000. You might be wondering how come it's such a huge variation. Well, it has got to do with factors affecting their strength, which we will be talking about them later. Okay, so just be aware that these are called intramolecular interaction. Then of course, moving on, we have the other type of interaction. So for example, ion-dipole interaction. You'll be introduced to them later on. Yeah, so ion-dipole interaction is actually between ions. So in this case, we have cations, sodium plus, anions chloride. Okay, interacting with, in the case of water over here, is a lone pairs of electrons. It's not being drawn in, so you can draw them in if you wish to. Yeah, between the delta minus of the lone pairs of electrons. Yeah, you might be wondering how come there's a delta minus at the oxygen. So later on, we're going to introduce you to a concept known as electronegativity values. Yeah, so oxygen is more electronegative as compared to hydrogen. So therefore, in terms of the shared pairs of electrons between oxygen and hydrogen, the shared pairs of electrons will be closer to oxygen as compared to hydrogen. So because of that, oxygen will take on a permanent partial negative charge. Yeah, and in that sense, it will interact with anything that is positively charged. Yeah, so for example, if you dissolve sodium chloride in water, yeah, the delta minus on oxygen will interact with the sodium plus, and the delta plus of the hydrogen will interact with the chloride. Yeah, so for the case of the chloride, you might also want to draw in the lone pairs of electrons. Yeah, so to make it more convincing. Yeah, so that you know that in terms of ion-dipole interaction, where they are really interacting towards or with one another. Okay, there's also something known as hydrogen bonding. So again, I will not go into details. You will be introduced to them later on. Yeah, so these are all categorized under what we call intermolecular forces of attractions. Okay, so I'm just going to write it out. Intermolecular forces of attraction. Okay, so you might want to copy it down. You might be wondering, what about ion dipole interaction? Yeah, so ion dipole interaction is also some form of intermolecular forces of attraction if you want to put it. Yep, and over here, I might as well just mention this because along the way, a lot of students ask, because they learn it a little bit different maybe in secondary school. Yeah. So sometimes in secondary school, your teacher might tell you that, for intermolecular forces of attractions, there are different types. Yeah. So they might break it down into different categories for you. If they do that, then good. It will be easier for you right now. Yeah, but if they don't, then don't be afraid of anything, because as I mentioned, it will be good for you to relearn everything. Yeah, just forget about everything you learned in secondary school and relearn it here. Yeah, so in case your teacher broke it down into the different types of intermolecular forces of attractions, you might be introduced to this term known as instantaneous dipole-induced dipole interaction, or some JC will call this temporary dipole-induced dipole interaction, or instantaneous temporary dipole-induced dipole interaction whatsoever. Okay, so they all mean roughly the same thing. So basically, they are due to the random fluctuation of the electron cloud, which give rise to some uneven distribution of electron density within a non-polar electron cloud. Yeah, so because of that, it gives rise to this kind of weak interaction. Yeah. Okay. So of course, we're going to talk more about that in the relevant section. But I thought I just want to bring you to your attention this particular term. Yeah. So over here, right, in our lecture notes, or even in the course of our tutorials or our class exercise or even assessment, right, you are free to use a slightly more simplified term to describe instantaneous dipole-induced dipole interaction. Yeah. So this simplified term, we call it dispersion forces. Yeah, it has actually a fuller name. It's known as London dispersion forces. Yeah, but it's perfectly fine if you simply just use dispersion forces. Yeah, excuse me. Yeah, it actually helps in writing, because dispersion force is just 2 words, but instantaneous dipole-induced dipole interaction is a long term. Of course, if you wish to use instantaneous dipole-induced dipole interaction, you are free to use it. Yeah, but of course, over here we are just saying that London dispersion forces or dispersion forces is actually okay to be used. Yep. Next, we're going to go on to 1.2. So for 1.2, we have electronegativity value. Yeah, so as what you might be introduced towards the end of atomic structure. So electronegativity of an atom is the ability to attract the electrons in a covalent bond to itself. Yeah, so basically a greater tendency to attract the shared pair of electrons. Okay, so because of that, it gives rise to an uneven distribution of electron clouds. Yeah, of course, in the case of hydrogen, both atom being the same, right? So it's equal sharing. But over here we are talking about, say, H2O or HCl. Like for example, in the above we have H2O over here. So oxygen is more electronegative than hydrogen. Yeah, so that means that the electron cloud will be sort of displaced towards oxygen. Yeah, so it will have a permanent partial negative charge. Then hydrogen will have a permanent partial positive charge. Okay, yep. So what actually affects electronegativity value? So in general, you will learn that electronegativity value increases across the period. Why is that the case? Okay, so the reasoning is given in your notes. Because the nuclear charge increase, shielding effect remain relatively constant. Yeah, so because of that, across the period, effective nuclear charge increase. So because effective nuclear charge increase, electronegativity value tends to increase across the period. Yeah, what about down the group? Despite experiencing roughly similar effective nuclear charge due to the increase in the number of principal quantum shell, the electronegativity value in general decreases down the group. Okay, so it can be summarized using this particular electronegativity scale. Yeah, so this is actually developed by Linus Pauling. You could actually just Google it on the internet, and you will find different types of electronegativity scale, but in general we are using the one by Linus Pauling. Okay, yeah, so also a little bit of background is that electronegativity values are not provided in the data booklets. Yeah, and there isn't a need for you to memorize them. Okay, so maybe just let me repeat. There isn't a need for you to memorize electronegativity value. Yeah, just take note of the general trends in electronegativity across the periods. Okay, so as we mentioned earlier on, increases across the periods and decreases down the group. I think this will be sufficient. Yep. But for the purpose of chemical bonding, especially later on when you're learning intermolecular forces of attraction, in particular hydrogen bonding, I tend to advise students to remember the electronegativity values of 4 elements. Yeah, just 4 elements. Knowing these 4 elements will actually help you quite a bit. Okay, so I'll just highlight them. Yeah, so it will be good for you to know the electronegativity value for hydrogens. Yeah, so the electronegativity value for hydrogen, right, is the lowest amongst all the non-metal. Yeah, so you might just want to sort of remember that, so 2.1. Okay, do take note of fluorine as well. It's the most electronegative element known to mankind, so it's 4.0. Okay, and of course oxygen 3.5. Okay, so it will be good for you to know carbon as well, 2.5. Okay, and of course nitrogen. Yeah, so other than that, other than these 5, right, the rest I don't think you need to remember them. Okay, and before you criticize that what I mentioned earlier on, because remember I said that you do not need to remember any electronegativity value, but right now I say, oh, you'll be good to know these, right? Okay, so the reason being, as some of you might know, when you learn certain ideas or certain concept, right, you can't go into discussion by simply just saying that, oh, you know, like this is roughly like this or what. It's good for you to have some numbers at the back of your mind to play around with. So it's the same as electronegativity value. Okay, so although you do not need to memorize them, it'll be good for you to know a few of them. But you do not need to intentionally memorize them. Okay, just take note of their values, because as you go along the way, as you progress through your chemical education in the next 2 years, right, you'll just naturally remember some of these values. Yeah, so you do not need to consciously remember them, but just take note of them at the back of your mind whenever you review the concepts. Okay, so of course here we said you do not need to memorize them, but it'll be good for you to know some values, and do not literally just memorize them off the table. Yeah, just as you go along your education, it will just come to you naturally. Okay, yeah. So how are they related to chemical bonding? So if you are looking at similar electronegativity values, so again, it also depends on how you interpret this term similar. Yeah, how similar is similar, so we'll deal with that later. They tend to be covalent in nature. So if there's a large difference in electronegativity values, it tends to lead to some form of an absolute electron transfer. Like for example, the electronegativity value of sodium is 0.9, that of chlorine is 3.0. So if you're kind of like expecting a covalent compound between sodium and chlorine, then you are quite not right, because as chlorine approaches sodium, it will just simply grab the electrons, the valence electrons from sodium. And knowing that sodium has an electronic configuration of 1s2, 2s2, 2p6, 3s1, and that 3s electron is very loosely held by looking at the ionization energy value, it can easily be lost to chlorine. Yeah, so in that sense, the nature of the bonding between sodium and chlorine will be ionic in nature. Okay, yep. Then I think over here we have 2 general bullet points. Covalent bonds are formed between non-metals of similar electronegativity value. Ionic bonding occurs between elements with large difference in electronegativity. Yeah, so I think it might be better for you to know that ionic bonding occurs between elements with large electronegativity difference. The reason why we put here metal and non-metal, right, is really just to sort of bring you to something that is quite familiar to you from secondary school. Because in secondary school, your teacher might tend to tell you that, oh, you know, the bonding between metals and non-metals are ionic in nature. But this is actually not true. Yeah, because there are a lot of metal, non-metal covalent bonds. Yeah, it is not a mistake. There are a lot of metal and non-metal covalent bonds. Then you might be wondering, so when is it covalent or when is it ionic? Okay, so in general, because now we are looking at the extreme scenario. Yeah, so in secondary school, when you learn chemical bonding, especially ionic bonding, you tend to learn the two extreme on both ends. Like for example, group 1 and 2, and then bonds with, for example, groups 16, 17, and 18. And because they are the two extremes, so you are expecting the bonding to be more or less a complete or a near complete kind of ionic bonding. Yeah, and because the electronegativity difference is just so huge, yeah, so you expect more or less a complete electron transfer. Yeah, but when you are dealing with, say, the transition elements, yeah, for example, somewhere in the middle, or the D block element, their electronegativity value tends to be a little bit on the high side for metals. Yeah, so when they interact with non-metals, the interaction could be more covalent-like rather than ionic-like. Yeah, so do not need to worry so much, because a lot of it you're going to deal with them only in university. You will also be dealing with metal, non-metal, covalent bonding in the last topic of your JC2. So that will be next year, May. Yep, but in the meantime, do not be too worried about that. Just get your fundamentals of covalent, ionic, and metallic bonding right, and then the rest will fall into place. As I mentioned earlier on, there isn't a need for you to rush into understanding every single thing. Okay, so I will move on to the next part. I think we are done with 1.3, and then for table 2, it showcase some trend in period 3 elements. So very clearly, sodium, magnesium, aluminium, they are metal, so it's not very different from what you learned in secondary school. Silicon is a semi-metal, otherwise known as metalloids. Okay, do take note that for silicon, the structure is giant molecular, or what we call giant covalence. Okay, it's not giant metallic. Yeah, so do take note of the terms being used to describe the structure. So for sodium, magnesium, and aluminium, it will be giant metallic. Okay, and then from phosphorus all the way to argon, we are looking at simple molecular structure. Okay, for the case of argon, you need to be a little bit more careful. We are looking at monoatomic, or otherwise we call it simple atomic. Yeah, I think the easiest way is to call it monoatomic, because as we know, noble gases have the octet configuration. So in the case of argon, the outermost configuration, the valence configuration, is 3s2 3p6, so it doesn't have a tendency to form a covalent bond with other atoms, so it doesn't have a tendency to share electrons. Yeah, but later on you will learn that for elements, for noble gases such as xenon, there are actually many compounds it can form with. That's because for xenon, its valence shell is period 5. So for period 5, then there is more room for the expansion of octet, because it is able to allow more atoms to surround it. Yeah, so we are looking at steric consideration. Yeah, but at this moment, you do not need to be too worried about those exceptions. Okay, yeah, so basically this table just showcased to you how the trend in intramolecular bonding changes across period 3. So it goes from metal to non-metal. Okay, and then of course the types of structure goes from giant metallic to giant molecular to simple molecular. Yeah, it will also be maybe worth mentioning that for the simple molecular structure for phosphorus, sulfur, and chlorine, for phosphorus it exists as P4, sulfur as S8, chlorine as Cl2. Yeah, but at this juncture, we do not require you to remember the molecular formula. Yeah, so do not stress yourself up regarding all these details. Yeah, just be aware that they don't exist as diatomic, like most of the gases you're familiar with. For example, you know that hydrogen is H2, oxygen is O2, fluorine is F2. Yeah, so you might be thinking that phosphorus might be P2, but it's actually P4. And as to the actual explanation, it has got to do with energetics consideration. That will be topic 5. So in topic 5, you'll be doing some calculation to sort of verify that why phosphorus prefers P4 rather than P2. But we will not go into details at this moment. Okay, so with that, let us take a look at exercise 1.1. So we are supposed to identify the types of chemical bonding in the following. It will definitely help if we have a periodic table with us. So first of all, 1.1a, we look at barium. Barium is group 2, so over here. So it should be a group 2 metal. So then it will be very clear cut. So the types of chemical bonding will be metallic bonding. So we'll just write it as metallic bonding. Okay, then for oxygen, or sometimes we call it dioxygen, is in group 16 over here. Yep, so that will be simple molecular. So simple molecular, that means that within oxygen molecule, we are looking at covalent bonding. Okay, so it will be covalence in nature. Yeah. Then for barium oxides, it represents the extreme ends. So for barium is over here, oxygen is over here. So you would expect almost an electron transfer from the 2 valence electrons of barium all the way to that of oxygen to give O2 minus, and O2 minus has an octet configuration. So with that, barium oxide, we expect ionic bonding. Okay, so ionic bonding will be the most straightforward answer. Yeah, nothing very much has changed from what we learned from secondary school. So remember that in secondary school, when we are looking at group 1 and group 2, okay, forming compounds with group 16 and 17, in almost all cases, we are looking at ionic bonding. And I think in secondary school, that is the usual saying that metal, non-metal will usually give ionic compounds. Yeah, the reason being because the first 2 groups, group 1 and group 2, they have very low first and second IE. So first group very low first IE, second group very low first and second IE. And for group 16 and 17, they are desperate for electrons in order to attain the octet configuration. So in the words of energetics, we will say that they have pretty low electron affinity. So they have affinity for electrons. So in that case, gaining electrons is pretty easy for group 16 and group 17 elements. So because of that, we expect just a direct electron transfer from group 1 or group 2 to group 16 and group 17. Yeah, so because of that, we are expecting more of ionic compound rather than covalent compounds. Okay, then for NO2, this is nitrogen dioxide. So again, for nitrogen dioxide, we are looking at group 15 and group 16. So in this case, 2 non-metals. So based on what we learned from secondary school, if you remember how to draw the dot and cross diagram, but you're not expected to do it now. So if you can remember, then you will know that in order for the central atom to have the near octet configuration or octet configuration, then sharing of electrons will be a more prominent route, because for 2 non-metals, you do not expect any form of electron transfer because you do not expect them to have low IEs. Yeah, and of course they have some affinity for electrons as well. So because of that, usually within non-metals, because of a very small difference in electronegativity, you expect some form of covalent bonding. So in this case, we expect NO2 to exist as simple discrete molecules. So of course within NO2 molecules, we expect covalent bonding. Okay, yeah. So over here, it's written, maybe I should say as a side remark, but it is something you need to recognize for H2. It is possible for metal and non-metal to form covalent bonds. Yeah, so aluminum chloride is often an exception that is often mentioned for H2. Okay, but I wouldn't say it's an exception, but it is simply because if I can just scroll up a little bit, you notice that for aluminium, it has relatively high electronegativity value for a metal, and then for chlorine, its electronegativity is not very high. It's 3.0. So you expect aluminum chloride to have a very polar covalent bond. Yeah, so later on you will learn that if aluminum chloride were to exist as an ionic compound, if it were to exist as an ionic compound, the aluminum 3 plus having a relatively high charge density, it will polarize the chloride electron cloud to a very huge extent, and this strong polarization will result in some form of effective overlap between the chloride electron cloud and that of the aluminum 3 plus cation. So because of that, it looks more like a covalent compound, or a very polar covalent bond, rather than an ionic compound. Yeah, but do not worry so much about that right now, because I'm just preempting some of the concepts or ideas that you're going to learn in the future. Yeah, so I think at this stage, if you do not understand a lot of what was being said, I think it is still okay. Yeah, I mean, in a sense that, as I said, for this particular topic on chemical bonding, it does help if you keep revisiting it as you learn chemistry. Okay, so we have a last remark here. Most chemical bonds are neither purely covalent or purely ionic. Okay, is it possible to have a pure covalent bond? The answer is yes. Between two atoms with no electronegativity difference. So that is, for example, between two hydrogen atoms, or between two oxygen atoms. So once you have atoms that are different, we call them heteroatoms, there are bound to be some form of electronegativity difference, and then because of that, you will end up with some form of polar covalent bonds. If not, to the other extreme will be an effective electron transfer, giving you an ionic bonding. Okay, yeah, so do not worry so much. If you want to, you can look at section 7, but you do not need to do that now. Okay, so the next section we're going to look at is section 2 on metallic bonding. Yeah, but maybe I'll be direct over here. For metallic bonding in H2 chemistry, it is not very different from what you expect or what you learn from secondary school. Yeah, so most of you will be quite comfortable with section 2 on metallic bonding, because you will recognize that it is quite similar to what you learn in secondary school. Okay, so basically you need to recognize that, or you need to be able to say that or describe metals as having a giant metallic lattice structure. And then within the lattice structure, you expect metal cations being surrounded by the C or D localized electrons. Yeah, so the electrostatic forces of attraction between the cation and the C or D localized electron, that gives rise to the metallic bonding. So in another sense, right, metallic bonding is what we call non-directional. Okay, why is it non-directional? Because the C or D localized electrons are free to move around the whole ionic lattice, or metallic lattice, So because they are free to move around, and at any one point in time, it's able to form some form of electrostatic forces of attraction with any nearby cations. So you do not expect the cation, you do not expect the interaction to be of a certain direction. So it's what we call non-directional bonding. Yeah. Okay, so I think what I've mentioned is so-called described in this particular paragraph over here. So what you need to take note of is that the metal is electrically neutral. So therefore, if you are asked to sketch out maybe just a bit of a structure, or just to sketch out what you expect the structure and bonding to be in a typical metal, for example calcium, you need to make sure that the positive and the negative charge balance out. So that means that you will need to count the electrons. So over here we have 6 calcium 2 plus. So when you are drawing it, just make sure that you have a total of 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, just make sure you draw that out. Some of you might argue that is that really very important, because we are just capturing a snapshot of otherwise a very big piece of metal. Yeah, so the truth is, it's not that important, I have to admit. Yeah, however, right, whenever you present your answer, right, it has to be as close to the reality as possible. meaning that my metal must be electrically neutral. Yeah, so it is of course important for you to be conscious about balancing the positive and negative charge. Okay, the strength of the metallic bonding is related, but not directly related. Okay, it's related to the number of valence electrons per metal atom. So you would expect the metallic bonding to be stronger in magnesium as compared to that in sodium. Yeah, because the number of electrons being contributed to the COD localized electrons for magnesium is 2, whereas that for sodium is 1. Okay, so you expect stronger metallic bonding within magnesium as compared to that within sodium. Okay, another factor has also got to do with the charge and radius of the metal cation. So that is what we call charge density. Yeah, so charge density is basically the charge over the ionic radius. Yeah, so the larger the charge density, the stronger the metallic bonding. Yeah, so that is something perhaps you need to be aware of. Yeah, but you also need to know that the charge density is not so much of charge over ionic radius. Yeah, so sometimes students have the misconception that it is equal. It is not equal. It is actually equal, so-called, we are actually looking at the surface charge density. Yeah, that means that we are assuming that the ion is like a sphere. So we are looking at the charge density distribution on the surface. Yeah, so over here is defined for you. It's the amount of charge per unit surface area of the ion. Yeah, so that is what we are looking at, and what we are focusing on. So if you are actually very specific and serious about this, right? Actually, we are really looking at the charge density is actually proportional to ionic charge divided by r squared. Yeah, because you know that surface area is, if you assume it's a perfect sphere, that would be 4 pi r squared. So I think ionic charge over r squared might be better. But we can always simplify the situation by looking at the charge over the radius. Okay, so that's just for a simplistic discussion. It is perfectly fine for H2. Okay, so moving on to 2.3, we are looking at the physical properties of metal. Yeah, so again, not very different from what you learned in secondary school. So we're looking at high melting point, boiling point. Why is that the case? Because of the extensive as well as the strong metallic bond within the metallic structure. Okay, so remember that whenever you describe why is it that the melting point or the boiling point is very high, right? You need to be able to phrase it out in this sense. You need to say that stronger the metallic bond, you need more energy to overcome the metallic bonding. That leads to higher melting and boiling point. Yeah, you notice that we use the term overcome. We don't use the term break. Yeah, sometimes you might hear chemists or even your teachers say that you are breaking the bond, you are breaking the bond. The word break is actually a colloquial term used by chemists. We don't actually break a bond because a bond is not a physical object. Yeah, it is a bond is actually the forces of attractions between opposite charges. So normally we say that you overcome the forces of attraction rather than breaking the bond. Yeah, but you can still say break because it is so ingrained in the literature or in the language of chemists that it is used synonymous to overcome. Yeah, but the right term to use is actually overcoming forces of attraction or overcoming the bonds. Okay, with that, we'll come to exercise 2.1, which is a work example. So over here, you are required to explain why the melting point of magnesium is higher than that of sodium. So you notice that it's 650 degrees Celsius, sodium is 98 degrees Celsius. So you need to quote relevant data from data booklets. So what is the main thing you need to discuss? I think number one, you should be able to come up with this idea. Yeah, remember we mentioned that earlier on. For every one magnesium atom, it contributes 2 valence electrons to the COD localized electrons, but for sodium only 1. Yeah, so you expect from here the metallic bonding within magnesium to be more extensive. Yeah, and in the case of Mg2+, it has a greater charge, and a smaller ionic radius. So you need to quote this ionic radius. Whereas for sodium, bigger ionic radius, smaller charge. So you expect Mg2 plus to have a higher charge density than sodium plus. So because of that, more energy is required to overcome the stronger metallic bonding within magnesium as compared to that in sodium. So therefore, the melting point of magnesium is higher than that of sodium. Yeah, so that is the logical thought processes you need to be able to understand. But you also need to be aware that when a solid metal melts and become a liquid, right, the metallic bonding is still present. It's just that it becomes weaker. Yeah, so just like, you know, when you overcome the bonding in a solid structure, after the solid structure collapse, there is still some forces of attractions between the molecular form if you are talking about molecular solids. Yeah, it's just that it is weakened. Yeah, so it's the same case as metal. So it is only until when it boils that we are looking at a fully overcome the metallic bonding. Yeah, so that's the origin of why we incorporate a useful information for all of you. Okay, for good metals, we all learn from secondary school that they are good electrical and thermal conductors. That's because they have mobile charge carriers or charge mobile carriers. Yeah, so either in the form of electrons or ions. So because of that, if you apply a potential difference, you expect electrons to delocalize from where the potential is higher to where the potential is lower. Yeah, so the delocalized electrons also assist in the conduct of heat. Okay, so the thermal energy allows the electrons to move or delocalize more quickly. So in that sense, the energy is transferred from one end of the metal to the other end. Okay, so with that, we have exercise 2.2. Why does copper wire conduct electricity when a potential difference is applied? So we look at option A, bonding electrons in the crystal lattice move. Okay, so if you take a look at the paragraph above, the electrons are acting as mobile charge carrier. So it's over here. So if you just read 2.3.2, then I think you will immediately think that option A is the answer. So indeed, option A is really the answer. However, right, as per all MCQ, it's important for us to take a look at the other options as well. So for option B, copper 2 ions move to the cathode. If you remember what you learned under electrochemistry in secondary school, right? A cathode is negatively charged and it attracts cations. So B seems to make a little bit of sense because if you think about it, indeed, this also involved the movement of ions. Yeah, but we need to take a look at what the question really wants. The copper wire conducting electricity. So this is the main thing we need to deal with. Okay, so later on I will draw a diagram to illustrate it. Hopefully it will make things a little bit clearer. And then C, the atoms of copper become ionized. So this is what happens at the anodes. Okay, when the impure copper gets oxidized. Yeah, so this is what C means. So copper goes from copper solid to copper aqueous. So C actually means this. Copper solid, it gets oxidized at the anode, so it will go into the solution as copper 2 plus, and then the 2 electron will flow through the wire. And then D, the crystal lattice breaks down. So what kind of crystal lattice are we talking about? Are we talking about a metallic crystal lattice? So probably it has a similar meaning to that of C, but it's not a very clear, it's a very vague answer. It's a very vague kind of response. Okay, then why are we so sure that A is the answer? So this actually touched on a little bit of your knowledge from secondary school electrochem. Yeah, so since we put this as an example, so perhaps let me explain it in detail. So if you remember your electrochem in secondary school, so maybe I'll just use the space here, right? So this is the battery. Okay, so the battery actually provides the electromotive force, so plus minus. Okay, so we connect like this. Okay, so over here we have the cathodes. So this is the, okay, so I'll just label this in blue. So this is the cathodes. This is the copper cathodes. So this is the Cu cathodes. I just put Cu cat. Okay, and then the other sides, maybe I'll just draw a weird looking structure, something like this. This is the impure copper. Okay, so I'll just put this as the copper anodes, ANODE. Okay, and then I'm just going to draw the solution that they are being placed in. So this is just a solution. So in most cases, we are actually looking at copper sulfate solution. So this is just copper sulfate aqueous. Okay, so if you remember what you learned in electrochem in secondary school, right? When the circuit is being closed, the copper anode will be oxidized. Okay, so the copper at the surface will go into the solution as copper 2. So you enter the surface as copper 2 plus. Okay, and then at the cathodes, copper 2 will be deposited. Yeah, so this is essentially how the purification of copper will work. Will you also learn this in A levels in H2 Chem? Yes, you will learn it. It should be under topic 20 or 21 under electrochem. Yeah, so so B and C sort of describe this particular process in the solution. Yeah, but this process, right, is not the movement of electrons. So you don't see or you do not observe electrons moving through the solution. What happens is that the ions migrate across the solution. But what exactly is happening to the copper wire is that electricity is being driven across the wire. Yeah, so in that case, the best answer to, or rather the only correct response to exercise 2.2 will then be option A. Yeah, because the rest of the option doesn't make sense at all. It doesn't make any sense when we are dealing with the stem of the question. Why does copper wire conduct electricity? So we are looking at the copper wire. So specifically, we are looking at this particular copper wire. Okay, so this is the wire that they are talking about. So you have to be very careful when you're answering the question, because a lot of the students have the misconception that the electrons move across the solution during electrolysis. Yeah, so hopefully next year when you move on to JC2, you will not have this misconception. Okay, but not to worry about it in JC1 right now. Okay, so if the electrochemistry stuff I talk about sounds very alien or very foreign to you, I think you can just ignore them for now. But I thought that, you know, in the discussion of this exercise, I just want to keep it complete. Okay, I will move on to 2.3.3 on malleability and ductility. So I don't think I need to go through this in details, because you would have encountered this in secondary school as well. So basically, metals are malleable and ductile. So malleable means can be beaten and rolled into sheets. Ductile here means can be easily drawn into rods, wire, tubes. Why is that the case? Because if you try to apply a little bit of force and cause it to sort of deform, right? You notice that the attraction between the cation and the delocalized electron remains. Yeah, so they remain very, very strongly attracted, because remember, metallic bonding is non-directional. So as long as the sea of delocalized electrons is surrounding the cations, right, then metallic bonding exists. Yeah, so in that sense, even when we roll them into rods or try to flatten them, it wouldn't break. Of course, when you make them thin enough, it will break, because I mean, once you make it atomic thin, then it has no choice but to break into two separate pieces. Okay, so that is something that you need to be aware of. And then of course, hardness. Hardness of a material depends on how we can move the particles from their fixed position. So it depends on the strength of the metallic bonding as well. So usually metals are hard. Unless we are looking at group 1 and group 2, they are quite soft. You can actually cut them with a penknife. Yeah, so especially for sodium, like metals such as say sodium or lithium or potassium, right? If you watch some of the YouTube videos, you notice that they are usually kept in oil. So when they are taken out from oil, they can be cut using just a penknife. You don't really need a specialized tools to cut them. Okay, and then of course for application for metals, in order to increase their hardness. We are looking at alloys, because for the case of alloys, we are incorporating different metals together so that it is not so easy for them to slide past each layer. Okay, so so for example, for a normal for a metal with similar atoms, when you apply a stress across, you will just you expect the layers to slide past each other. But let's say in between I have some impurity atom. The atoms has a different size, so when you apply a force, it's not so easy for the layers to slide past each other. Yeah, so that is the advantage of having alloy, so that it actually increase the hardness of the materials. Okay, then with that, we're going to move on to section 3 on ionic bonding and physical properties of ionic compounds. You will notice that a lot of the ideas that are presented in this particular section will be very familiar to most of you, if not all of you, because the learning objectives for ionic bonding for H2 chemistry is pretty much similar to that in secondary school chemistry. The only difference is that you are being taught a relationship that links lattice energy to charge and the ionic radii. And lattice energy over here is used as a proxy to the strength of the ionic bonding. Okay, so yep, this particular section begins by introducing you what ionic compounds is, quite similar, and of course sodium chloride is used as a typical example. You have the space filling model as well as the expanded model. One of the most common misconception students have on ionic bonding, maybe I should just stress upon this over here. One of the most common misconception for ionic bonding is that the students tends to have an impression that the lines drawn here are the ionic bonding only. Okay, so for example, if you are looking at, let's say, sodium, the one that is black, that the smaller black sphere, okay, you tend to think that, okay, it's interacting with a chloride above, it's interacting with a chloride behind it, it's interacting with a chloride in front of it, to its right and to its left, and then below it. So you tend to have the impression that there's a total of 6 ionic bondings, or 6 ionic bonds. This is absolutely incorrect. Okay, so maybe I should write it down. Maybe in secondary school you thought that the sodium plus forms 6 ionic bonds with 6 chlorides. Okay, now, and maybe I should put only. Yeah, then I think it's easier to correct the misconception. This is entirely incorrect. Yeah, so let me reiterate. This is entirely incorrect. What is correct is that the 6 nearest oppositely charged partner, they are chlorides. This is correct. Yeah, but it does not only form 6 ionic bonds. Okay, sodium plus forms an infinite number of ionic bonds, because similar to metallic bonding, ionic bonding is non-directional. Yeah, so this particular sodium plus, right, it can form ionic bonds also with chloride that are far away, except that it's not very strong. So for example, you cannot deny this particular interaction, you cannot deny this particular interaction, or even a chloride that is very far away. Yeah, it's still, the interaction still exists, it's just that the interaction is weak. Yeah, so please do not have this misconception that the number of ionic bonds, right, it appears to be what is being shown to you in the diagram. The diagram can be misleading, but it's not so much of the diagram's fault, but sometimes it's the way we understand it, or maybe sometimes it's the way in secondary school, maybe it has been simplified, and because it has been simplified, you might have the wrong impression that it is as what was mentioned, but it is not. I hope everyone, after listening to me on this, you do not have the misconception that based on the diagram, this is the number of ionic bonds it can form. Okay, it is incorrect. Remember that ionic bonding is non-directional. I think it's being emphasized here. It is non-directional. Okay, extends infinitely in all directions. The only directional bonding that we are aware of that is of importance is covalent bonding. Okay, over here we have some background information on coordination number. Okay, so basically what we mentioned earlier on regarding sodium chloride, I think it's easier to discuss coordination number based on sodium chloride. So for example, for sodium plus, we say that it has a coordination number of 6. That means that it's surrounded by 6 chloride ions. And then of course chloride will have a coordination number of 6 as well. Okay, so this is the number of ions of opposite charge surrounding a central ion. And this is known as coordination number. Yeah, we are not able to predict coordination number by just looking at the formula and of course trying to decide how many. It is not possible. So for example, zinc sulfide coordination number 4, and then sodium chloride is 6, but for cesium chloride is 8. Yeah, it is almost impossible to kind of like predict the coordination number. What you could do is to look at experimental data, okay, and sometimes we look at X-ray diffraction data lah. I mean, that is not within the scope of the H2 curriculum. Okay, the table 3 over here just gives you the number of ions, and a good proxy will be it is related to the size of the cations and anions lah. Yeah, I think a simple example I can use here will be say sodium chloride versus cesium chloride. If you look at your periodic table, sodium is over here, cesium is 2 positions below. So obviously cesium is much bigger than sodium plus in terms of the cationic size. So because of the difference in cationic size, I would expect more chloride to be able to surround a cesium cation as compared to a sodium cation. Of course, this is all factors being equal because over here we are simply just understanding the fact based on the chloride surrounding the sodium plus forming ionic bonding. Yeah, but in reality, for example, if the anion is a polyatomic anion or is some other forms of anions that is able to form bonding other than ionic bonding, for example covalent bonding, then the steric factor itself. Okay, so when we are looking at size, actually what we are looking at is steric factor, which you'll be introduced to in organic chemistry. Yeah, so that usually reasons other than steric factor is known as electronic factor, and they tend to play a more important role in deciding the coordination number. But for a simple ionic compound, just between cations and anions, ionic in nature, using the size can be a good proxy lah. But of course in H2 Chem we are not expecting you to know that. Okay, so you don't need to memorize the coordination numbers for any of the ionic compounds. Yeah, so over here we have some bullet points going through. So for example, the size is important, okay, as well as the relative charges. So a cation with +2 charge will require twice the amount of anions with -1 charge. So the way it's being arranged around the central atom will be a little central ions will be a little bit different. Okay, as mentioned earlier on, we use lattice energy as a proxy for determining the size of the strength of ionic bonding. So you will learn this under energetics. So the definition is over here. Lattice energy defined as a heat evolved. It must be heat evolved solely by the definition. Okay, why is that the case? I'm going to write out a chemical equation just below, but let us read through the definition first. It's defined as a heat evolved when 1 mole of pure ionic compound is formed from its constituent gaseous ions. So for example, let me use sodium chloride as an example. So we are forming 1 mole of solid sodium chloride. Okay, and lattice energy is defined as a heat evolved when 1 mole of this is formed from its constituent gaseous ions. So the constituent gaseous ions of sodium chloride is sodium plus and chloride minus. Okay, and they exist in vacuum. So can you just imagine they exist in vacuum, infinite distance from one another. Now I put them very, very close to one another. Okay, and the electrostatic force of attraction becomes stronger and stronger and stronger. And by forming electrostatic force of attraction, otherwise called ionic bonding here, the system will be releasing heat or releasing energy in the form of heat. Yeah, and therefore lattice energy is inevitably a exothermic term. So definitely heat is evolved only. You don't need to take in energy to form bonds. Remember this. Okay, so lattice energy kind of define the ionic bond formation for ionic compounds when gaseous ions are being forced closer and closer together. Eventually you form the solids. Okay, so I thought this part is worth mentioning, so we spent a bit of time talking about it, and the understanding is of extreme importance. And of course, over here, this equation is not exactly written for you for this chapter, because I think, as you have seen from the learning objective, it's actually under energetics. That will be topic number 5. Yeah. As of now, you don't really need to write this equation, but if you want to just write it for some reference, I think you could write it in. So we can compare the strength of ionic bonding using lattice energy. So the greater the magnitude of the lattice energy, the more heat is evolved, and you would expect a stronger ionic bonding. Okay, and this particular relationship is, of course, very important. I think I mentioned it at the beginning of this chapter. So lattice energy is directly proportional to the product of the charges, inversely proportional to the sum of the ionic radii. So the sum of the ionic radii includes the ionic radius of the cation and that of the anions. Okay, so therefore, the larger the charge and the smaller the radii of the ions, the greater will be the magnitude of the lattice energy, and this will imply a stronger ionic bonding. Yeah, and do take note of this. This is a proportionality relationship. So lattice energy is proportional to the products of the charges. Remember this, the products of the charges, and inversely proportional to the sum of the ionic radii. Yeah, so if you want to write it out in words instead of equation, you need to phrase it properly. Okay, so 3.3 gives us some physical properties of ionic compounds. They tend to have very high melting and boiling point, as seen from the data. So for example, sodium chloride is the one with the lowest melting point. It can go as high as like 2,852 for magnesium oxide. Are there ionic compounds with low boiling point or melting point? Yes, there are. So they are known as ionic liquids, but we will not be talking about them under H2 chemistry. Okay, if you are interested, you can go and find out a little bit more about ionic liquids. Okay, so with that, let us discuss exercise 3.1. Explain why magnesium oxide has a higher melting point than sodium chloride, quoting relevant data from the data booklets. Okay, so over here, so we are comparing between magnesium oxide and sodium chloride. Okay, so now we are looking at the data from our data booklet. So for magnesium 2+, we'll just summarize O2 minus, Na plus, Cl minus. We summarize the ionic radii over here. So remember this particular relationship, you need to quote it when you're answering the question. Yeah, so in terms of the product of the charges, okay, for MgO, so that will be -4, but the product of the charges for sodium chloride is -1. Yeah, so in terms of the product of the charges, Q plus multiplied by Q minus, it is numerically larger than that of sodium chloride. Okay, what about in terms of the sum of the ionic radii? So 0.065, if you sum it up with 0.140, so you get about 0.205. Okay, this is obviously a numerically smaller number than that if you try to sum up 0.095 and 0.181. Yeah, so because of that, in terms of the sum of the ionic radii, for MgO, it is smaller than that for sodium chloride. Yeah, so therefore I expect the lattice energy for magnesium oxide to be larger in magnitudes as compared to that of sodium chloride, simply because for the product of the charges, it is larger than that of sodium chloride, and the sum of the ionic radii is smaller than that of sodium chloride. Yeah, so because of that, I will need more energy to overcome the stronger ionic bonding within MgO as compared to that within sodium chloride. So this will result in much higher melting points. Yeah, so this is the way you go about deriving your answer. You'll notice that it is a very systematic step-by-step way of analyzing, and towards the end, or at the end, the conclusion is always related to the fact that you need more energy to overcome the stronger interaction, and that will lead to a higher melting point or boiling point. So this is the usual strategy we go about in answering questions related to melting boiling points. Okay, the next section is on electrical conductivity. Yeah, so pretty much similar to what you learned in secondary school. So for solid states, they are non-conducting because the ions are in fixed positions, not free to move. Because remember, one of the criteria is that you need free mobile ions. In molten and aqueous states, the free mobile ions is available. So if you apply a potential difference, you expect the ions to move from one end to the other end, or the electrons to be okay, sorry, in this case there's no electrons. Okay, so you expect the ions to move. Yeah, so because of that, you expect conductivity for ionic compound in its liquid or molten phase, as well as when it's in the aqueous phase. Okay, yeah. Electrical conductivity of aqueous solution increases as its concentration goes up. I think this is inevitable because there are more ions to carry the charge. Okay, can? Yeah. Then under 3.3.3, they tend to be hard and rigid. Okay. However, rigid also means that it is brittle. Why is that the case? Because if you apply a force to it, for example, this particular crystal, it's good on its own, but when you apply a force to it, the plane will slide past one another, and then after that, over here, you get all the charges that are alike, and therefore they will repel each other, and the repulsion will cause the crystal to shatter. Okay. What about solubility? This is actually a more complicated section. Yeah, so they are usually soluble. In secondary school, you learn about ionic compounds, like the solubility rules, right? For example, you learn things like, oh, all chlorides are soluble except silver chloride, lead chloride, and perhaps mercury chloride. Yeah, you learn them without understanding why. Yeah, so we will not go into details over here, except to maybe point to you to go to section 12 to look at an explanation on the solubility of ionic compounds, and it will be a lot clearer when we are discussing delta G, the Gibbs free energy, under topic 5 in energetics and thermodynamics. Yeah, so for now, I think we can KIV the idea of solubility first until we reach section 12 as well as topic 5 under energetics, thermodynamics. Okay, so with that, we have come to the end of the lecture on the first 3 sections. So for the next lecture, we will be discussing covalent bonding.